Welcome to this video, where we're going to take a look at surds and where I hope to be able to help you understand these better as part of your A-level maths studies. So let's ask the question, what is a surd? A surd is an expression that involves a root symbol. This may be a square root symbol, a cube root symbol, and so on. Although the majority of the surds that you'll see at A-level will involve square roots, you do need to be able to deal with other roots as well, if only occasionally. So typically a surd will look something like the square root of 5, the square root of 17, the cube root of 4, and so on. There are some laws or properties of surds that you'll need to be familiar with for your A-level maths course. These are, for square roots at least, the square root of a times b is equal to the square root of a times the square root of b. Here we require a and b both to be greater than or equal to 0, since we don't want to be trying to take any square roots of negative numbers, at least in this video. The next law is the square root of a divided by b equals the square root of a divided by the square root of b. In this law we require a to be greater than or equal to 0, but b to be strictly greater than 0. And for both of these laws, we will usually consider a and b to be integer valued in this video, though arguably they don't have to be integer valued. We also have for square roots and for a greater than or equal to 0 that a is equal to the square root of a times the square root of a, which is equal to the square root of a all squared. In other words, the square root of a number a is that number which, when multiplied by itself, is equal to a. And this is of course written as the square root of a. There are similar rules for nth roots, but these are rarely used at A-level. However, I do include these later in the video. And note that we do not have in general that the square root of a plus b is equal to the square root of a plus the square root of b, for example. This is a very common mistake that people often make when dealing with surds. Suffice it to say that this is not a rule of surds. We can see that this is not true if we simply take a is equal to 16 and b equal to 9, because in that case we get the square root of a plus b is equal to the square root of 16 plus 9, which is the square root of 25, which is equal to 5. But on the other hand, we have that the square root of a, which is the square root of 16, equals 4, and the square root of b, which equals the square root of 9, which is equal to 3, giving the square root of a plus the square root of b is equal to 7. And last I heard, 5 is not equal to 7, so in general, we don't have that the square root of a plus b and the square root of a plus the square root of b are equal. They might be equal in some very specific and particular cases, but generally they're not equal. The kinds of surds that we're interested in this video are those which can be simplified, but also, in particular, those which can be simplified but where the root symbol cannot be completely eliminated. For example, the expression the square root of 144 is a surd expression since it contains a root symbol. But since we know that the square root of 144 is just 12, then this symbol, the square root of 144, can just be replaced by 12, and thus the root symbol has been completely eliminated. We can already deal with these kinds of expressions, these are nothing new. But if we consider something like the square root of 98, then this can be simplified, but even after simplification there will still remain a square root symbol. So let's have a look at some simple examples of how these laws or properties of surds can be used to simplify some surd expressions. Simplify fully the square root of 252 divided by 81. So using the rule, the square root of a divided by b is equal to the square root of a divided by the square root of b, then we have that the square root of 252 divided by 81 is equal to the square root of 252 divided by the square root of 81. So we can split this into two separate simplification problems. On the one hand, the square root of 252, and on the other hand, the square root of 81. Now clearly the square root of 81 is equal to 9, so that was an easy one. But how about the square root of 252? Well, for this we need to identify the largest square number which divides 252. So the number, this divisor that we're looking for, can't be bigger than half of 252. So it can't be 144, for example. It's not 121. 100 doesn't divide 252, nor do 81 or 64 or 49. However, 36 does divide 252, so that 252 is equal to 36 times 7. So therefore, the square root of 252 is equal to the square root of 36 times 7. And now, using the rule, the square root of a times b is equal to the square root of a times the square root of b, we get that the square root of 36 times 7 is equal to the square root of 36 times the square root of 7. And since the square root of 36 is equal to 6, then we have that the square root of 252 is equal to 6 times the square root of 7. And so the square root of 252 divided by 81 is equal to 6 root 7 divided by 9. And finally, we can cancel the common factor of 3 in the numerator and denominator to give 2 root 7 over 3, which is fully simplified. In fact, in this particular problem, there was some cancelling that could have been done right at the very start, since 252 over 81 can be cancelled down to 28 over 9, and which would have potentially reduced the amount of work to do. But don't worry if you fail to see some cancelling out that can be done at the start. We all do it from time to time, but the important thing is that whatever cancelling can be done gets done somewhere at some point during your solution. Also, generally speaking, when you want to simplify a surd, such as the square root of n, then ideally, and to minimise the work that you'll need to do in order to simplify the expression, you really need to identify the greatest square number which divides n. So suppose that p squared is the greatest square number dividing n, so that we have n equals p squared times q. Then we'll have that the square root of n is equal to p times the square root of q. And since p squared was the greatest square number to divide n, then we can be sure that the square root of q will be as simple as possible and won't require any further simplification. So on to the next problem. Expand and simplify the expression square root of 5 plus 3 root 15 times 5 root 15 minus 6 root 5. So we've been told exactly what to do here, so we just need to go ahead and do it and get started. So we get, after expansion, 5 root 75 minus 30 plus 225 minus 18 root 75. And so by collecting like terms, we get 195 minus 13 times the square root of 75. But of course, the square root of 75 is a surd which can be further simplified, and you need to make sure that you do this further simplification, because we get that the square root of 75 is equal to the square root of 25 times 3, and using our laws of surds, we get that this is equal to the square root of 25 times the square root of 3, which of course is equal to 5 times the square root of 3. And so our original expression is equal to 195 minus 65 root 3. We expanded, we simplified, we got the answer. Veni, vidi, vici. However, there is another way to simplify this expression, which I personally think is probably a bit quicker. So bearing in mind that often when you need to simplify expressions, it will usually be as part of your solution to another problem, where you are the one who has to decide how you want to go about simplifying the expression. So here we go. We can recognise that the square root of 15 is equal to the square root of 5 times the square root of 3, which means that our original expression can be written as root 5 plus 3 root 5 root 3 times 5 root 5 root 3 minus 6 root 5, where we can take root 5 out as a common factor from each set of brackets as shown on the screen. And so we end up with 5 times 1 plus 3 root 3 times 5 root 3 minus 6. So then we just expand the brackets and continue the simplification. And for me, this is a bit quicker, personally. Nevertheless, whether it's quicker or not is not really important. What's important is that you understand what you're doing. And the more possible ways you have to approach solving a problem, the more likely it is that you do understand what you're doing. So let's have a look at a further example. And in my solution to this next problem, I'll be a bit more thorough with my explanations. The solution that I give is my solution, the solution that I happened to choose at the time of making this video, and there's no suggestion that this is the only way or the best way of solving this problem. It's really up to you to decide for yourself what you consider to be the best way of solving a given problem, and it's very rare for there to be only one way to solve a problem. So here we go. Write the square root of 37 minus 10 root 12 in the form a plus b root 3, where a and b are suitable integers. So clearly, we have a square root under a square root, so we're going to have to be a bit more careful about how we go about this. I want to isolate the expression underneath the main square root symbol. In other words, the expression 37 minus 10 root 12. So here, I might have to be prepared to try some different possibilities. But the first thing that I want to do is to simplify that square root of 12 to give root 12 is equal to the square root of 4 times 3, which is root 4 times root 3, which of course is equal to 2 root 3. And so the square root of 37 minus 10 root 12 becomes the square root of 37 minus 20 root 3. Now there's a dead giveaway here about what to do. Since I've been told to express my answer in the form a plus b root 3, then I'm looking for a way to get that main square root symbol to disappear. That would happen if the expression underneath the main square root symbol was an expression of the form, say, something squared. So my guess is to start with 37 minus 20 root 3 is equal to p plus q root 3 all squared. At this stage, there's no guarantee that what I decide to do will actually work. I've said in previous videos that I'm always prepared for an idea not to work. If it doesn't work, then it doesn't work. Move on and try something else. Don't fall in love with an idea so much that you can't admit that it's not working and allow yourself to try something else. So now expanding the right hand side gives 37 minus 20 root 3 is equal to p squared plus 2pq root 3 plus 3q squared, which gives some simultaneous equations to solve, namely p squared plus 3q squared equals 37 and 2pq is equal to minus 20. And this second equation, of course, cancels to give pq is equal to minus 10. Of course, to solve these simultaneous equations, you could solve using a fairly routine method that you may have learned as part of your GCSE or A-level studies, but this will create potentially a lot of unnecessary work. But I see something easier. However, I do encourage you to try solving these simultaneous equations for yourself using a routine method and see for yourself why I've chosen not to go down that route here. And as you'll shortly see, I've gone for a different approach. Ultimately, it doesn't matter which approach you take, as long as you execute the steps correctly, then you will arrive at the correct result. But searching for more subtle approaches to solving a problem is often a good way to develop your problem-solving skills and understanding, rather than just relying on set ways of doing things. So my solution is this. Since we know that p and q are integers and p times q is equal to minus 10, then there are only a few options to try. There's the possibility that either p or q is equal to 10, but neither of these are going to work because if we look at the quadratic simultaneous equation, if p is equal to 10, we're going to get p squared is equal to 100, which is obviously greater than 37. And if q is equal to 10, then we're going to get 3 times q squared, which is going to be 300, which again is greater than 37. So I don't really need to consider the possibilities where either p or q is equal to 10 or even minus 10. So there are only a few other options to try. P equals 5 and q equals minus 2, p equals 2, q equals minus 5, p equals minus 5, q equals 2, or p equals minus 2 and q equals 5. And it turns out that either p equals 5, q equals minus 2, or p equals minus 5 and q equals 2 works. The other two possibilities do not solve the equation p squared plus 3q squared equals 37. So we have either 37 minus 20 root 3 is equal to minus 5 plus 2 root 3 all squared, or 37 minus 20 root 3 is equal to 5 minus 2 root 3 all squared. And so the square root of 37 minus 20 root 3 is either equal to minus 5 plus 2 root 3, or it's equal to 5 minus 2 root 3. But which one should we choose? The answer to that is that we need to think what the main square root symbol represents. Here it represents the positive square root. That is, the answer that we get, a plus b root 3, needs to be a positive number. Well, of the two possibilities, minus 5 plus 2 root 3 or 5 minus 2 root 3, only one is positive, and it's 5 minus 2 root 3. So therefore, the square root of 37 minus 20 root 3 is equal to 5 minus 2 root 3. So it's important that you get comfortable dealing with surds. You'll be expected to simplify surds when you see that they can be simplified, and you really should be able to do this without a calculator. You need to leave expressions in surd form really as a default and not replace them with decimals. Take your time and don't try to do too much in one go, especially when you're learning this stuff. For each step that you take, try to identify exactly which rule you're using, and if you're not able to identify which rule you're using, then you may be doing something wrong, or you may be trying to do too much in one step. But with regular practice, your confidence and along with it your speed will naturally increase. Don't try to force things to happen quicker. If you're making the effort to learn this stuff early in your course, then you won't have any problems. You will learn it. You just need to be patient and allow nature to take its course, so to speak. So now we come to the extra stuff part of the video, where anything goes. Here, I'll try to whet your appetite for more mathematics and discuss some things that, although not necessarily part of the A-level maths course, are nevertheless interesting if you're into that kind of thing, and may help you to appreciate and understand some parts of the A-level maths course better. So don't worry if you don't understand everything that I say in this part of the video straight away. You will most likely not be examined on most of this extra stuff. I include it because I would have found it interesting during my A-level maths studies, and so maybe some current A-level maths students may also be interested. So let's just have a look at some more laws of surds and some proofs of the laws which I gave you at the start of the video. So I've already given the laws of surds for square roots, but more generally for nth roots we have that the nth root of a times b is equal to the nth root of a times the nth root of b, and the nth root of a divided by b is equal to the nth root of a divided by the nth root of b, where a and b are of course suitable real numbers. For example, we don't want to be taking any even roots of negative powers here, and dividing by 0 of course is right out. The nth root of a number k is that number which, when multiplied by itself n times, is equal to k, and this is written the nth root of k. So now let's have a look at the proofs of the rules or properties of surds for the case of square roots. So we could use the rules of indices to derive the laws of surds. For example, we know from the laws of surds that a times b to the power of n is equal to a times n times b to the power of n. And so in particular, a times b to the power of a half is equal to a to the power of a half times b to the power of a half. But we also know that a times b to the power of a half is equal to the square root of ab. And similarly, a to the half is equal to the square root of a, and b to the half is equal to the square root of b, giving the square root of a times b is equal to the square root of a times the square root of b. And similarly for a divided by b all to the power of a half. However, we can also take a more from first principles approach, as follows. Recall that the square root of a number a is defined to be that number which, when multiplied by itself, is equal to a, and is written the square root of a. Also, a multiplied by itself can be written as the square root of a all squared. B can be dealt with similarly, in which case we have a times b is equal to the square root of a all squared times the square root of b all squared. And since the square root of a all squared means the same as the square root of a multiplied by itself, and similarly for the square root of b all squared, then we have that a times b is equal to the square root of a times the square root of a times the square root of b times the square root of b. And then we can use that multiplication is commutative, which is a posh word meaning that we can change the order of the numbers that we're multiplying together to give that a times b is equal to root a root b times root a root b. And inserting brackets gives root a root b in one set of brackets times root a root b in another set of brackets, which is just root a root b multiplied by itself, and which can otherwise be written as root a root b all squared. And so by taking square roots of each side, we have that the square root of ab is equal to the square root of a times the square root of b as required. And of course the case the square root of a divided by b equals root a divided by root b can be shown in a similar way. And the more general case for nth roots proceeds along a similar line of reasoning. So I've spoken about irrational numbers in another of my A-level videos, and much of what I say in that video about irrational numbers is applicable to surds, since surds tend to be examples of irrational numbers. In particular, the square root of 2 and the square root of 3 are irrational numbers. And moreover, for an integer n, then the square root of n will be irrational whenever n is not a perfect square. So that brings us to the end of this video. There's a bit more to cover on the subjects of surds, particularly rationalising the denominator, which I haven't included in this video, but I will be making a separate video on shortly, I hope. I hope that you found it useful and interesting. If you did, then please hit the like button to show your support, and don't forget to subscribe to my channel. I'll be uploading more videos to this channel covering more A-level maths topics over the coming weeks and months. If there is anything that you'd like to ask about anything in this video or about mathematics in general, please send me an email or leave a comment in the comments section. Thank you for watching, and I'll look forward to uploading the next video. Do zobaczenia wszyscy. Pa!